Hello everyone, welcome to Tuteetute. In this particular video, we will see about the normal incidence. So, it is about the propagation of the electromagnetic wave from one medium to another medium. So, we will take, this is the boundary which is separating two media. So, medium 1 we are taking here and this is medium 2. And this is not line, this is the plane actually. Okay, this is a surface or plane which is separating two media, that is medium 1 and medium 2. And medium 1 characteristics are given by mu 1, epsilon 1, sigma 1. That means medium 1 containing the permeability mu 1 and permittivity epsilon 1 and conductivity sigma 1. Similarly, we can take here permeability mu 2, permittivity epsilon 2 and conductivity sigma 2. Like this we can take. And using these values we can get the impedance that is represented with eta 1 for the medium 1, and the impedance here it is given by eta 2. Like this we can take. Okay. So eta 1, eta 2 are the impedances of medium 1 and medium 2 respectively. So here we are incidenting one electromagnetic wave from medium 1 to medium 2. We are sending like that. That means the wave has been incident on this particular interface. Okay. So this is the plane. So that plane we will take as XY plane. So this is x-axis and y-axis is coming out of the screen. So this is external like this, okay, and this is the z-axis. So we are following right-handed coordinate system. So y is coming out of the screen, x is this side. So we are closing the fingers like this, means from x to y we are closing. So thumb is representing the direction of propagation. So our z-axis, so that we can able to represent like this. So what is the meaning of normal incidence? Incidence means generally electromagnetic wave we are sending like this onto the interface. So the interface is, this is the plane. Okay, and for that particular interface, what is the normal? Normal means generally perpendicular. So normal means I will take like this. So this z-axis itself is normal to the interface. Okay, interface is this one, that is xy plane. X-axis, y-axis is coming towards you. So xy plane is the interface. Okay, and normal to the interface is z-axis like this. Okay, now what is this normal incidence? Means what is electromagnetic wave we are incidenting that is parallel to normal to the interface. Okay, so already normal is making 90 degrees. So whatever the incident wave is there, that should be taken like this. Okay, so we can able to tell the electromagnetic wave has been incident on the surface here normally, because we have taken two impedances or two different media. Okay, here this is one media represented by the impedance eta 1. This is another medium represented by impedance eta 2. Two different media means surely two different impedances will be available. So because of the impedance mismatch, we can able to tell certain portion of this one will be reflected back. Whatever the incident power is there, out of total incident power, because of the impedance mismatch, eta 1, eta 2 are different. So certain power will be reflected back. Remaining will be transmitted into the another media. So like this, the things will be done. Okay, this is the incident wave and this is the reflected wave and this is the transmitted wave. Whatever is reflected, whatever is transmitted is also electromagnetic wave. You are incidenting the electromagnetic wave. What is transmitted this side, that is electromagnetic wave. What is reflected again into the medium 1, that is also electromagnetic wave. That means in medium 1 we are going to deal with two electromagnetic waves. Okay, these two, that means incident wave and reflected wave, both are available in medium 1 only. And this particular wave, that is transmitted wave, is related to medium 2. That means here it is related to the impedance eta 2 and this incident wave and reflected wave are related to eta 1 because of the medium 1. Okay, then here again I will draw that particular diagram. So this is the x-axis, the y-axis is coming out of the screen, so xy plane is the interface and z-axis is this one, and this is a normal to the interface, that is z-axis only. Like this we will take. So electromagnetic wave, about that one we know already some basics. So electric field and magnetic field and the direction of propagation, these three must be mutually perpendicular. So by satisfying that one, how to draw here the electromagnetic wave representation, that means electric field, magnetic field and the direction of propagation, these three we should indicate clearly. So as I said, this is medium 1 and this is medium 2, and here it is represented by impedance eta 1, here it is represented by impedance eta 2. Okay, now what I will do in the sense, the wave has to be incident on the surface, so I am concentrating on here this incident wave. So this is related to incident wave. So this is the direction of propagation. Okay, this is the direction of propagation. So electric field and magnetic field should be perpendicular to this direction of propagation of this incident wave. So electric field I will orient in the x direction. So EI, I refers to incident wave. Okay, so EI is the electric field of the incident wave that is oriented in the x direction, and wave is propagating in the z direction. So what is the orientation of the magnetic field? It should be y direction. So it should come out of the screen. That means how to take that one? We have to mention like this. Dot circle represents that particular magnetic field is oriented towards y direction only. Here already we have indicated y is coming out of the screen, so that we have to represent like this. So this is the way of representing the incident wave. It is propagating towards z direction, electric field is oriented in the x direction and magnetic field is oriented in the y direction. Okay, then it is incident on the xy plane, that is the interface, and here because of the impedance mismatch, eta 1 is different from eta 2, so certain portion of this particular signal will be reflected back and remaining portion will be transmitted into the medium 2. So now we will concentrate on the reflected signal. How this particular wave will be there? So reflected signal. Okay, so we are clearly saying that we have incident on the interface. Okay, that means it is traveling in the z direction. That's why the arrow is represented like this. Because of the impedance mismatch, the wave is reflected back. That means it is entering into medium 1 only. It is traveling in the medium 1 only, but opposite direction to incident wave. So this is the direction representation of the reflected wave. And we will assume that there is no change in the orientation of the electric field. So this is the reflected electric field. For the reflected signal, whatever the electric field is there, that one we are representing with the ER. And to satisfy the right-handed coordinate system, how to represent now the magnetic field? So generally this is the direction of propagation. So here in this way, if you rotate your fingers like this, this should be representing the E2H. Then thumb is representing the direction of propagation. First you see again the incident wave. So in the incident wave, the thumb is representing the direction of propagation, means that should be towards z direction. So E2H. So this is the E field. Already we have represented. So H field should be available towards U. So we are closing like this. Okay, we are closing. This is representing the electric field and it is coming to the magnetic field, and thumb is representing this particular z direction. Or we can use the three fingers like this. Okay, thumb is representing the direction of propagation, forefinger is representing the electric field, and middle finger is representing the magnetic field. Or we can tell like this: if you close from the electric field to magnetic field, the thumb will represent direction of propagation. Now this one I have told for the incident wave. Now coming to this reflected wave, already two things are fixed. One is direction of propagation is towards negative z direction and electric field is oriented in the x direction. Okay, so how to represent the magnetic field? Means you see here, thumb is already I have kept in the direction of the propagation, and this fingers also I have kept in the direction of the electric field. So now I have to close like this. Okay, then what is the meaning of that one? Magnetic field is going into the screen. That means we have to take cross circle. Dot circle represents coming out of the screen, and cross circle represents going into the screen. So here H bar represents into the screen. That means negative y direction. Okay, or you can able to represent using these three fingers also. So thumb represents direction of propagation, forefinger represents the electric field orientation, and middle finger is going into the board. That means that is the magnetic field representation. This is the representation of the what we can say incident wave, and this is the representation of the magnetic wave. Okay, this is the incident wave, this is the reflected wave. Like this we can able to represent. Okay, so the incident wave is going towards the z direction like this by orienting the electric field x direction, and magnetic field is in the positive y direction. And in this way we can able to represent the thumb is towards negative z direction. That means it is a reflected wave, and forefinger is again representing the this x direction only. That means electric field is in the x direction, and magnetic field is going into the board. That means negative y direction. That is what we can able to tell regarding the reflected wave. Now the transmitted wave. Transmitted wave, after incidenting this electromagnetic wave onto this one, already I have said that because of the impedance mismatch, something is reflected, remaining will be transmitted into the medium 2. That means here also it is traveling towards z direction only. So there is no change in the electric field orientation. That means it is a transmitted signal, ET again towards x direction only, and magnetic field is coming out of the screen. That means like this, HT. Okay, so you can able to see one thing for the incident wave, and this is for the transmitted wave I have taken. Okay, so transmitted wave and incident wave orientations are equal. Okay, electric field orientation and magnetic field orientations are equal, but if you see reflected wave, your orientation of the electric field is the same, but orientation of the magnetic field has been changed, and the direction of propagation is also changed. Okay, once you have understood this one, now we are going to apply boundary conditions. Okay, so from the previous diagram, quickly I will draw here. This is the surface we can able to take, x-axis and y-axis is coming out of the screen. This is the normal, that is z. So what we have taken here, incident wave can be represented like this. This is the reflected wave orientations, and this is transmitted wave orientations. Okay, this is HT, HR, this is HI. So we know the boundary conditions generally. So on the boundary, if you assume there is no charge and there is no current, so the tangential components of the electric fields and the tangential components of the magnetic fields are continuous, provided I have already said that there is no charge on the surface and there is no current also. Okay, that is what we need to take. Even charge is there, the tangential components of the electric field are continuous only. So that we can able to take the equations like this. E tan 1 is equal to E tan 2. Because there is no current, we can take HT1 is equal to HT2. So what is the meaning of this one? Tangential component of the electric field in medium 1 is equal to tangential component of the electric field in medium 2. And here also tangential components of the magnetic field in medium 1 is equal to tangential component of the magnetic field in medium 2. That is what we need to take. So, but in medium 1, okay, this is medium 1 and this is medium 2. In medium 1, we are dealing with two signals. One is incident wave, second one is reflected wave. So here we will get two electric fields and two magnetic fields. But in medium 2, we are dealing with only one signal, that is a transmitted signal. So only one electric field is there and only one magnetic field is there. So accordingly, we are going to use these particular equations. Okay, so that is what we need to take. So already the boundary is the xy plane. and this particular electric field is oriented towards that one only. So easily we can able to write the tangential components R can be given like this: EI plus ER is equal to ET. How did I write this one? Since we have here two waves, one is incident wave electric field is EI, and one more wave is also there, that is the reflected wave, its electric field is, here we have to take ER. Okay, so that is equal to, we can able to take transmitted signal electric field, that is ET. So here total tangential components of the electric fields are given by EI plus ER. Here tangential component of the electric field is given by simply ET. Okay, similarly we can write equation for the magnetic field intensities also, that is HI plus HR is equal to HT. Like this we can able to write. Okay, then we have relations of this electric field and magnetic field with respect to impedance. Okay, so from our basics we can able to write like this, that is electric field of the incident wave divided by this magnetic field intensity of the incident wave. This is equal to medium 1 impedance, because these two are available in medium 1 only. Okay, then we can able to take like this also, that is ER, that means reflected wave electric field and reflected wave magnetic field, this is equal to minus eta 1. So these two are available in medium 1, so we need to write eta 1. But why minus means the direction of reflected wave is opposite to incident wave. So in order to mention that one, in order to take that particular condition into the account, we have to put here minus symbol. Okay, so this is very important. If you take the ratio of electric field and magnetic field, generally impedance will come, but whether it is traveling in the positive direction or negative direction, that is what we have to see. So compared to this one, compared to incident wave, the reflected wave is traveling in the opposite direction, that's why here minus sign is required. Okay, then we will take like this electric field and magnetic field ratio in case of the transmitted signal. That means related to medium 2, here it is given by eta 2, simply eta 2, because these two are related to medium 2, so suffix 2 we are using here. So using all these things, now we are going to get the ratio of reflected electric field and incident electric field, and one more ratio also we are going to get, that is the ratio of transmitted electric field and incident electric field. So by having these ratios, what we can able to get in the sense transmission coefficient and reflection coefficient. Okay, so that is what we will see here. So those equations I am writing once again. So EI plus ER is equal to ET. Next we got HI plus HR is equal to HT. This is equation 1, this is equation 2 I am taking, and I am going to use the related equations of the impedances. Okay, so this equation 2, now I am modifying like this. So this particular magnetic field of incident wave can be written like this, that is EI by eta 1. Okay, how did I write this one? Since EI by HI is equal to eta 1. So HI is equal to, I can write EI by eta 1. That is what I have written. Next, this HR can be written minus ER by eta 1. How did I write this one? Since ER by HR is equal to minus eta 1. So here we have HR, that is equal to ER by minus eta 1. That is what I have written here. So this is equal to HT. HT is nothing but, now can be written like this, ET by eta 2, because that is related to medium 2, we have to write like this. So this is equation 3. Now we have to solve. Okay, using equation 1 and 3, we can get the ratio of ER and EI, that is one ratio, and second ratio is ET and EA. Those things we have to get. Okay, so substitute this particular, if you want the ratio, that is ER by EI, so we need to eliminate ET. So what we need to do? So I am taking this entire signal, so EI by eta 1 minus ER by eta 1. Okay, this is equal to, ET means what we can take here from this equation 1, we can take EI plus ER by eta 2. This is what we can get. Okay, now the equation is available in terms of EI and ER only. We have eliminated ET. Okay, So what we can do now, wherever the EI terms are there, you take common. So EI, if you take common, 1 by eta 1 minus 1 by eta 2. And if you take ratio, eta 2 minus eta 1 by eta 1, eta 2 will get. This is equal to, by sending this ER term to this side, so ER times of 1 by eta 2 plus 1 by eta 1, that is eta 2 plus eta 1 by eta 1, eta 2 will get. Okay. So eta 1, eta 2, eta 1, eta 2 will be cancelled. So what we will get now finally? So ER by EI is equal to, okay, what we will get? Eta 2 minus eta 1 by eta 2 plus eta 1. So this is what we will get. So this is actually given by gamma. Gamma means what? Reflection coefficient, that is ratio of reflected electric field and reflected electric field and this incident electric field. Okay, so this will give how much amount of reflection is there compared to incident wave. So you are sending certain amount of incident electric field, out of that one how much is reflected back is given by this particular gamma representation, and this equation was given in terms of simply impedances of the two media. Okay, so if you have eta 1 and eta 2, you can able to tell if you send certain amount of incident wave, how much can be reflected back. That information we can able to easily get by using this particular formula. Okay, then we need to get one more ratio, that is ET by EI. So now again you see equation 1 and equation 3. Now replace this ER now, okay, in terms of ET. So that particular analysis I am doing here now. So see carefully, EI by eta 1, this ER we have to replace. So minus 1 by eta 1 I am writing first. Next ER can be written from the equation 1, that is ET minus EI. So ET minus EI. So this is about this particular term. That is equal to, we can write now ET by eta 2. So like this we can write. Okay. So wherever EI terms are there, you write it one place and take EI is common, and ET also you can able to take common and get the ratio of ET and EI. So first I will write here about EI. So EI I am taking common. So 1 by eta 1, and here also you are getting minus into minus is plus. So you will get 1 by eta 1. So 2 times of 2 by eta 1 will get. Like this will get. So it is equal to, here ET by eta 2 is there. ET by eta 2, and here what we will get? Minus ET by eta 1. So by sending that one this side, 1 by eta 1 we will get. So 1 by eta 1 plus 1 by eta 2, that will give eta 2 plus eta 1 by eta 1 plus eta 2. So here this eta 1 will be cancelled. So finally we need ET by EI. So this is equal to, what we will get? This one should go this side. That means 2 times of eta 2 by eta 2 plus eta 1. Like this we can able to write. Okay. So this itself is called tau. That means transmission coefficient. So now for the normal incidence case, when you incident the electromagnetic wave normally to the surface or to any what we can tell, to the any plane, to any boundary, then how much amount of electric field can be reflected back, or how much amount of electric field can be transmitted into the other media out of the given incident electric field is given by these two. Okay, by having this particular reflection coefficient in terms of the electric field, we can tell how much is reflected back, and using this particular transmission coefficient formula we can tell how much can be transmitted into the medium 2. Okay, so that is what we can able to tell, and easily these formulas are given in terms of the impedances only. Okay, so very simple thing. Okay, if you have the impedances eta 1, eta 2, easily you can able to tell, and this particular formula you can able to compare with the transmission line analysis also. So you take one particular transmission line having the load impedance is ZL and its characteristic impedance is Z0. What is the reflection coefficient here? Gamma, that is equal to ZL minus Z0 by ZL plus Z0. This formula is comparable to this formula only, na? Okay, here two media are there. We have taken two media, and medium 2 can be directly taken as the load with respect to medium 1. That is what we have to take. So eta 2 minus eta 1 by eta 2 plus eta 1. These are the impedances only. And here also in the transmission line analysis also we can take impedances only. Okay, there we have defined this particular reflection coefficient, and here also we have defined reflection coefficient, and here you can able to define the transmission coefficient also. Okay, so using this particular analysis we can able to analyze how much amount of power or electric field or magnetic field also we can able to analyze how much is reflecting back and how much is transmitted because of the impedance mismatches. Okay, so this is the theory regarding this particular normal incidence. Thank you.